we're going to finish the Dolev-Strong protocol, and then next week, so after we finish this, like we've seen our first consensus protocol, like we kind of understand, you know, how to model and reason about distributed consensus protocol. So we'll talk about the suggested lab, like basically the simulator for consensus protocols, right? So I will first help you recall the protocol which we talked about at the end of last lecture. So in the Dolev-Strong protocol, initially everyone's extracted set is empty. So the extracted set maintains my belief about what the sender wants to send to everyone. So the extracted set can contain 1 bit, 2 bits, or no bit at all. Okay, so remember F is the number of corrupt players and N is the total number of players. And now the protocol works as follows. In the first round, which I denote as round 0, the sender signs its input bit, which is B, and he sends the signed bit to everyone. So this denotes signature, right? Remember, we basically, without loss of generality, we are going to assume the sender is node number 1, player number 1. Okay, so this means signed by the first node. Now, for each of the remaining rounds, and in particular, we are going to run the protocol for F+1 round. And if we are, you know, in round R, what you want to do is to look for either bit that has gained at least R signatures from distinct players. So if I have received at least R distinct signatures, R signatures from distinct players for some bit B. Okay, actually, let me write it slightly more nicely. From distinct players for some bit B. And actually, let me use B prime just to differentiate from the sender's input bit, right? So remember the sender's input bit was B. So let me use B prime. And moreover, so not only do I need to count at least R signatures, it also must be the case that 1 out of the R signatures must be signed by the sender itself. So it needs to be at least R signatures, 1 of which comes from the sender. And in this case, I will check to see if B prime is already in my extracted set. Okay, so if it's not in my extracted set, right? If it's already in my extracted set, I don't have to do anything. But if B prime turns out not to be in my extracted set, the first thing I will do is to add it to my extracted set. And then the next thing I will do is I will add my signature to B prime, basically. I will sign the bit B prime, and I will basically forward B prime, as well as all the signatures I've seen on B prime. And I send all of this to everyone else. Can I ask one of you to mute yourself? I think there's street noise. Okay. So this is basically, you know, when I add it to my extracted set, what I want to do is I want to convince everyone else to do the same, right? So the reason for forwarding my view or my knowledge to other players is because, you know, we are required to have consistency in the end. So whatever I know, I want to make sure everyone else knows. Okay, so this helps. Oops, this helps to make sure that everyone else also knows this. And then we essentially run the protocol for F+1 rounds. And at the beginning of round F+2, I will look at my extracted set. And then if the size is equal to 1, then essentially I'm just going to output the bit that's in my extracted set, because this is, you know, what I believe the sender wants to send. you know, in some cases, the extracted set can have nothing. Like for instance, if the sender is malicious, he didn't send anything. If the sender didn't sign anything in particular, then my extracted set can be empty. The sender can also be malicious. If the sender is malicious, maybe he will sign both bits, in which case it's possible that my extracted set will have both bits, right? But regardless, as long as the extracted set is not of size 1, I'm just going to output a canonical bit 0. So that's the protocol. Any questions about the protocol? Okay, so if no questions, the first thing we want to think about, actually before that, what I want to mention is, like, you know, it helps to think about if the sender is honest, what will be actually the behavior of the protocol, right? If you think about it, if the sender is honest, what happens is that the sender will send the input bit B in the first round, and then everyone will receive it at the beginning of the next round, right? So at the beginning of round 1, everyone will have seen the sender's signature on B, and everyone will add B to their extracted set in round 1. So yes, I guess, like, because I'm naming the first round round 0, it's a little confusing. So maybe I should just say round 0 and round 1. So in round 0, sender sends its bit, and everyone adds it to the extracted set in round 1. And because the sender is honest, it will never sign the other bit. So at the end of the protocol, no one will have the other bit in their extracted set. So, you know, in this case, we can see that the protocol works very well, and, you know, everyone outputs the sender's input bit B at the end of the protocol. But of course, as we said, you know, when the sender is honest, that's not really the interesting case, right? The more interesting case is what happens when the sender is actually corrupt. In that case, we still want to guarantee consistency. Okay, so one question, as I asked last time, is why does the protocol need to be run for f+1 rounds? Like, what if I don't want to run it for so many rounds, right? Let's say I just run it for f number of rounds. Okay, so again, if you think about it, what's happening in this protocol is that I'm modifying my belief of what the sender has told me, you know, and the belief is maintained by the extracted set. As I modify my belief, I always want to let everyone know, you know, I've modified my belief, and here's the reason why I modify my belief. And if I do that, you'll be convinced to modify your belief too, you know, if you have not done so yet. So in some sense, the more rounds, like intuitively, the more rounds you have, like the kind of, you know, you're kind of in some sense amplifying consistency, but that's not very precise, obviously. That's just intuition. Okay. So can anyone spot an attack, let's say, that breaks consistency if we run it for only f number of rounds?
Like in the last class, we noticed, like, when the sender, let's say you have total odd number of nodes, and the designated sender partitions the remaining nodes into two equal size sets and sends 1 bit each, and then all the other f-1 corrupted senders do the same thing.
You mean the sender sends 0 to this
and
half and 1 to the other half, and then what do the other f?
Other f-1 do the same thing. They send 0 to the left half, 1 to the right half.
F node send 0 to here and 1 to here.
Yeah.
Is that, which round is this in? I guess, like, it matters.
No, so f-1, all the subsequent rounds, that is the behavior of the other compromise nodes. So,
okay, so
any honest nodes in those two halves, they'll they'll think that they have
so let's say there's
0
one honest
and
node
1.
here and one honest node here. So this is one honest and this is the other honest. Okay, in the first round, the sender sends 0 to this half and sends 1 to the other half, right? So this half will add 0 to their extracted set, and this half will add 1 to their extracted set. Okay, and now in the subsequent f+1 rounds, you are seeing all these corrupt nodes, they sign 0 and send it to this honest person, and sign 1, send it to this honest person. So now, in some sense, in round F, but I mean, this person will also send 0, right? Like in round 1, when it adds 0 to its own extracted set, it will announce this to everyone else, you know, hoping everyone else will be doing the same. And then so is this direction. So in round 1, this honest person on the right will say to everyone, you know, I've added 1 to my extracted set, and here's why I've added 1 to my extracted set. So in fact, in this case, in round F, actually, because of this signature, these two messages, in fact, everyone will have both 0 and 1. And so we may need to like modify this attack a little bit to make sure actually you violate consistency. Yes.
What's the bet sent by the sender to those F-1 malicious player?
I guess it doesn't matter what the malicious players communicate among themselves, right? Because you can imagine all the malicious players, they form a single coalition and they can collaborate to perform the attack. And you know, we don't require consistency for the malicious nodes, because malicious nodes, they can do anything, they can output anything. You know, we cannot essentially require any security property for the for the corrupt nodes. So by the way, actually, if you don't mind, could you please turn on your video? I guess like I wasn't too sure who was speaking, answering the previous question, because I couldn't see you.
So I was wondering, like, maybe we can modify it so like in the beginning, the sender and the like dishonest, like the rest of the dishonest nodes kind of behave honestly, like they all send like, I don't know, like a 1 to everyone.
Okay, let's say sender and then plus, let's say F+1 other dishonest nodes. They send 1 to everyone. So
yeah,
this is honest.
And then they kind of behave honestly, more or less, for like the next rounds up until the last round. And then in the last round, they switch to say 0 for like some part of the honest nodes.
Oh yeah, that's a great attack. What's your name?
Lisa.
Lisa, can I spell it like this?
Yeah.
Okay, great. So let's look at Lisa's attack. Let me repeat what she said. So essentially, okay, imagine we divide the honest nodes into 2 camps. And let's say in round 0, the sender sends 1 to, let's say, all of the honest nodes, right? So what happens is that in round 1, everyone will add 1 to their extracted set. So, okay, so in round 1, what happens is that the extracted set has 1 in it. And then the protocol continues. I mean, when the honest nodes add 1 to their extracted set, I mean, of course, they're going to inform each other that they have done so, but, you know, because everyone has done that, you know, essentially, they'll receive the message, but the message doesn't trigger any more event. So now this continues. And then in the last round, which is round F, what happens is like here, you know, there are in total F corrupt nodes, right? So the F corrupt nodes can make F signatures on 0. So now suddenly they will send F signatures on 0 only to the right camp of honest nodes. So F signatures on 0. And this message is sent in exactly round F. So remember in the protocol, right, in round F, I'm looking for a bit that has at least F signatures, one of which must come from the sender. And this indeed satisfies that criterion. So what this group of honest nodes will do is that in round F, they will also add 0 to their extracted set. But now, you know, the issue is the protocol ends here. Like there's no time for these people to tell the people on the left that they have added 0. So if you make a decision at this point, you can see that the honest nodes will be inconsistent, right? So these people have 1 in their extracted set, so they'll output 1. However, the people on the right, they have both bits in their extracted set, and therefore they'll output the canonical bit 0. Okay, so I'll let you think about it a little more for maybe 30 more seconds, because this attack is actually very, very helpful for understanding not only why the protocol doesn't work, but also actually why the protocol works. We are actually going to gain intuition from this attack and then turn it into a proof of security for this protocol. So think about it on your own for 30 seconds and see if you have any questions about this attack.
Elaine, could you explain again, like if I see some inconsistency, so if I see a bit is signed by R people, and including one of them is the sender, then what will I do? Will I send the bit to the other one with all the people who signed this?
So when I send any message, I always send it to everyone, right? So we can look at, let's look at the protocol again. So essentially, the thing to keep in mind is if we are in round R, we want to look for R signatures, at least R. It can be more than R, but we want to look for at least R signatures on either bit. And if we have found R signatures on either bit, we are going to check if, you know, if I have this bit in my extracted set, because this is like, you know, a bit that many people believe in, right? So I want to make sure I'm consistent with other people. So if many people have signed it, and many, you know, the notion of many varies according to the round R. So in round R, many means R or more signatures. And basically if R or more people have signed it and it's not in my extracted set, I want to add it to my extracted set. But in order, you know, to have consistency at the end, when I add it to my extracted set, I want to be very careful. I want to say, okay, now I'm going to tell everyone immediately that I'm adding it to my extracted set. And here's an evidence that justifies this action, right? The evidence is I'm going to take all the signatures I've seen. I'm going to add my own signature, attesting to the fact that, you know, I've added to my extracted set. And then this collection of signatures will be able to convince, let's say, you to add it to in the next round if you haven't already added it.
Okay, so basically every round, if I add anything to my extracted set, then in next round, if we have next round, then everyone else or every honest player should add this to their extracted set. Okay.
Yes, so that is great. So we are actually, you know, as we analyze the protocol together, we are kind of getting to the proof. So you have stated the first claim we are going to prove, right? So let's write down the first claim we are going to prove. Okay. So we are going to prove that the protocol has consistency. And then in your homework exercise, you should prove that it also has validity. The validity proof is relatively simple. The consistency proof is also pretty simple, but I mean, it has more lines than the validity proof. Okay. So the first lemma, let's call it lemma 1. Okay, so the intuitive informal statement of lemma 1, I'll write down the informal statement and then I'll write down the formal statement. The informal statement is if I know it in round R less than or equal to F, then you'll know it in R plus 1. So if I know it now, you'll know it in the immediate next round. I mean, if there is a next round. If there isn't a next round, then, you know, sorry. Okay, so let's write down the formal statement. The formal statement is let R less than or equal to F if by the end of round R, some honest node I has B in its extracted set, in extracted I, then in round R plus 1, let's use B tilde. Let me say by the end of round R plus 1. By the end of round R plus 1, every honest player has B tilde in its extracted set. I'm just going to write extracted set. Okay. So we kind of already proved it together verbally, but let's just write down the proof again. There is actually one small subtlety to check, right? Okay, so if player I has B tilde in extracted I by the end of round R, what does this mean? This means, you know, player I must have added B tilde during some round, you know, earlier than R. I mean, either in round R or earlier than R. Okay, so in this case, let T be the round in which B tilde first got added to the extracted set of player I. Okay, so now let's think about the round T, right? So we know that in round T, I mean, T is at most R. In round T, player I adds B tilde to its extracted set. But remember in the protocol, okay, I'm scrolling to the protocol again. Remember in the protocol, as soon as I add to my extracted set, I will inform everyone else. And how do I inform everyone else? I send all the signatures on the bits that I'm adding to my extracted set, as well as my own signature. Okay, so how do I know this will convince others to add it in round R plus 1, if they haven't already added it? The thing to like realize is that this batch of signatures I'm sending has signatures essentially from R plus 1 distinct players. So in other words, the only thing I have to show is that when I add my own signature must be distinct from every other signature I've seen. And that's very easy to see, because if in the batch of signatures, let's say in the batch of R, at least R signatures I've seen, if there was my own signature in it, then this bit must have been added in an even earlier round, right? Because like I'm not going to sign it until I add to my own extracted set. Okay, so now the point is, okay, so basically player I must append its own signature to a batch of R signatures on B tilde and send the R+1 signatures on B tilde to everyone. Oh, sorry, it is not R. I'm confused. It is T. T+1 signatures on B to everyone in round T. And note, it is important to note that the signature, essentially, this signature on B tilde by the ith player, this signature must be distinct from all the T signatures player I has seen at the beginning of round T. Because if not, then player I would have added B tilde to its extracted set even before round T. Because if not, I would have added B tilde to extracted I even before round T. Okay, but by our assumption, right, we assume that T was like the round in which B tilde got added to extracted I. So now we can conclude by our network synchrony assumption, right? By network synchrony, whatever an honest player sends in round T will be received by all honest nodes at the beginning of round T+1. So by network synchrony, all honest players must have seen at least T+1 signatures on B tilde at the beginning of round T+1. So one thing actually I want to be slightly more precise is that player I must append its own signature to a batch of T signatures on B. In fact, it's actually at least T, right? It could be actually, the way we wrote the protocol, it can actually also be greater than T. And then this is also, it's at least T+1. This is actually also greater than or equal to. Okay. So therefore, everyone else will have added it to their extracted sets if they haven't already done so by the beginning of round T+1. Okay, so any questions for this?
Hi, yeah, I have a question. So there is no requirement for the signatures to be chained, right? They can be received in parallel or independently.
Yeah, they don't. It doesn't have to be chained. You can just sign the message separately. Yeah.
Also, one more question: is it fair to say that this has a denial of service problem, that even one bad node can pollute the extracted sets of every other node?
If the sender is honest, then yeah, actually that's a very good point. So I also have to not only, so you raise a very good point, right? So essentially when I say at least T+1 signatures, that's not enough, and I have to actually say one of them must come from the sender. I always forget to write that. One of the signatures must come from sender. And this is because like if player I added this in round T, so basically we said player I, it was even earlier. So player I must append its own signature to a batch of at least T signatures on B. And this also actually, I have to note, and moreover, one of them must come from the sender. Okay, yeah, so I always forget the sender part, but this may be related to our question. Like, let's say the sender is honest, and then, you know, we said if the sender is honest, the protocol has validity, so there should be no way for the adversary to like convince anyone to, you know, accept into their extracted sets the other bit, right? The sender, let's say, says 0, I shouldn't be able to convince you to add 1 to your extracted set. So if that's what you mean by denial of service, it's an excellent point. I always forget about this in my proof. Okay. Okay, great. So you also helped me correct the proof. And so now we are convinced that, you know, this nice property holds. If I know it now, you'll know it in the immediate next round. But this doesn't say, you know, like the issue is, what if there is no next round, right? What if like this is the next round? Can it happen that I happen to add something to my extracted set in the last round, but now I don't have an opportunity to tell you so you can add it? So how do we like overcome that? And if you, again, we went over this attack, and in fact, this attack exploits exactly this. Like if you think about the attack, what happens is that in the last round, some honest people add 0 to their extracted set, but they don't have time to inform other honest nodes to do the same. So the interesting thing is that actually the magic happens in the last round, the F+1 round. Okay, so now the second claim that we want to prove, and this is where the magic happens. Let me use the same numbering as in the textbook, lemma 2. So lemma 2 is like something magical. Basically, it says in rounds F+1, if I know it, you must know it. If I know it, you must know it now. So the difference between the two lemmas is like the previous one says, if I know it now, you'll know it in the next round. But here it's magical. It says in the last round, if I know it, you must know it now. And therefore we say like, essentially people reach common knowledge in the last round. So this is basically, you know, when we reach common knowledge. Okay, so now let me state this theorem a little more formally. Let me keep track of the time. I think we are on good time. So the formal statement is if some honest player I has B tilde in its extracted set by the end of round f plus 1, then every honest player must have it too. Must have B tilde in its extracted set by the end of round f plus 1. Okay. Okay, so to understand this, maybe we should turn our attention back to the attack, Lisa's attack again, right? So whatever reason why this attack doesn't work, had the protocol been run for f plus 1 rounds, that is actually precisely the reason why, you know, we can prove the second lemma. And so why is, I'll let you think about it for like 30 seconds yourself. Like, you know, if I had tried to make this attack work, but now the protocol is run for f plus 1 rounds, what will happen? Why doesn't the attack work if it's run for f plus 1 rounds?
You'll need f plus 1 signatures in that round to convince any node of any other signature. F
yes,
signatures
exactly.
you can get from dishonest nodes. The one signature you need to get from some other node. That some other node is honest, and to get its signature, it must have that bit in its extract set the previous round. And
yes,
by lemma 1, if that was true, then in this round anyway, all honest nodes will know that.
That's perfect. Yeah, that's exactly the answer I'm looking for. So let me repeat what Anoop said. Was that Anoop speaking? I couldn't see who was speaking actually.
Yeah.
Okay, great. Let me repeat what Anoop has said, right? So why doesn't the attack work if the protocol is run for f plus 1 rounds now and not f rounds? Because if I had tried to make the same attack work, right? Remember, you know, if you try to convince some people to accept 0, in the last round, you have to produce f plus 1 signatures. But, you know, how can you do that if you only have f nodes, right? The reason why the attack worked for the f round case was because I control f nodes and I have the capability to produce f signatures on 0 in precisely the last round. And therefore, if I tell, you know, half of the people, okay, look, here's f signatures on 0, and I do it like, you know, in the last round, then these people won't have time to inform others. Okay. So if we flip it around, it actually will be the proof. So let me first talk it over, and then I'll write down the formal proof, right? So what would the proof be? Like the proof would be, you know, if, let's say I add something to my extracted set in the last round, and now the last round is round f plus 1, this means I've seen f plus 1 signatures on this bit, but there are only f corrupt nodes. So if I've seen f plus 1 signatures, one of the signatures must come from an honest player, right? So if I receive this honest player's signature in round f plus 1, it means the honest node must have signed it in an even earlier round, right? So like, you know, I'm for the first time, you know, I'm adding this new bit to my extracted set, and what convinced me, you know, must contain at least one signature from an honest node. So that honest node must have signed it in an earlier round, and therefore when he signed it, he must have sent it to everyone else, and everyone else would also add it to their extracted set in the immediate next round, you know, by lemma 1, which we have just proved. Okay, so let me kind of turn this intuition into a formal proof. It's like almost exactly as what I said, and it's, you know, almost exactly the reason why the attack doesn't work. And so basically in the proof, we will consider 2 cases. Okay, so in the theorem, in this lemma, it says some honest player I has B tilde in its extracted set by the end of round f+1. So there are two cases. One is that I added B tilde to extracted I in some earlier round, let's say in round R less than f+1. So this is, let's say this is not added in the last round. I mean, this is the easier case, right? Like if some honest node added earlier, by lemma 1, this already took care of it. Like this bit must be in every other honest player's extracted set in the immediate next round. So in this case, actually lemma 1 just takes care of it. Okay, so the more interesting case is case 2. Case 2 is when player I added B tilde to extracted I in exactly the last round, in round f+1. And this is where the magic happens. So for player I to add B tilde to its extracted set in round f+1, it must be that I has seen f+1 signatures on B tilde from distinct players in round f+1 because there are only f corrupt nodes. There are at most f corrupt nodes, f corrupt players. One of these signatures must come from an honest node. Okay, so what does this mean? This means that at least one honest player has signed B tilde in some earlier round. In some round, R less than f+1. And now we go back to lemma 1 again. And now the lemma follows due to like what we proved earlier, due to lemma 1. Okay, so in the last round, something magic happens, and that something magic is just the pigeonhole principle, right? So all we are using is the pigeonhole principle here. Okay. I'll let you think about it for 30 seconds and see if you have any questions. So notice that this essentially gives consistency, right? So if lemma 2 is true, then it just means everyone will have the same extracted sets by the end of the protocol, and therefore they'll output the same bit. So this immediately implies consistency. And let me just write that. It is easy to see okay. Yeah, maybe I'll try to like scroll up a little bit. So now the case 2, which is the more interesting case, is centered on the screen. Okay, so if there are no questions, I just want to talk about an interesting puzzle, which is remotely reminiscent of the Dolev-Strong protocol. I mean, they're not directly related, but you'll see like why it's remotely reminiscent. And you might have heard of this. Actually, this is called the muddy children puzzle. So essentially, let's say there are n children, and they are playing outside in the playground, and the playground is muddy, and some of them have mud on their forehead. Okay, so after the play, the teacher gathered all the children together, and now the teacher announced, you know, some of you have mud on your forehead. And the point is like, you know, you don't have a mirror, so you cannot see if you yourself has mud on your forehead, but you can see every other kid, you know, everyone else, whether they have mud on their forehead. Okay, so now the teacher says, if you know you have mud on your forehead, please step forward. And let's say no one steps forward, and then the teacher pauses, and then now she says again, okay, now, you know, you can reconsider. If now at this moment you know you have mud on your forehead, now is your second chance to step forward. And then this goes on until, let's say, you know, in some round, some children step forward. So the question is, like, suppose there are K children who have mud on their forehead, right? Let's say K children are muddy. In which round will there be kids that step forward?
K round?
Is the puzzle clear? Should I repeat it?
Yeah, it's clear.
If it's not clear, you can shout out loud.
So do the kids communicate with each other that I see mud on your forehead or something?
No, no communication. Everyone remains silent. You can see whether other kids have mud on their forehead. You cannot see your own. And the only, you know, the only information you have is that the teacher said some kids have mud on their forehead. And you also know the current round, like, because the teacher will keep announcing, now try again, now try again, now try again. Right? Every time the teacher says try again, it's essentially a new round.
And the teacher has not explicitly specified how many kids have mud on there.
Yeah, the teacher doesn't say how many kids.
Okay.
And do the kids not talk to each other?
They don't talk. They just look at each other, and no communication allowed.
Wait, so what's the problem? What are we trying to do?
Once you solve this puzzle, you'll see why there's a similarity, I mean, remote similarity between this puzzle and the Dolev-Strong protocol.
So in each round, do the children who think that they have mud on their forehead, they basically step forward? That's all that happens.
Yeah, let's see the children, they're all rational. Like, they're perfectly rational. If they realize they actually have mud on their forehead, they will definitely step forward.
Yeah, so like I guess we can prove by induction, like it in K rounds it'll end, like if K is 1, then the kid who is muddy will see that no one has mud, so they'll realize that their forehead has mud because the teacher has said that at least someone has mud. So then they'll step forward.
Yeah, and if you build on induction, then it just follows.
Yeah, like the same argument follows. Like if at round n no one stepped forward and teacher asked for n+1 round, and you can see n others have mud, but only n others have mud, not more. That means you must have mud. So in n+1 you'll stand forward. So in K rounds, all the K children would have stepped forward.
Yes. Yeah, does everyone see it? Like, Anup gave a great answer. So it helps. You can just like, you know, start with K equal to 1. And if you see it for k equal to 1 and k equal to 2, then the induction is easy. If k is equal to 1, it's very easy, right? Because, you know, if I'm the only kid that's muddy, I mean, I see everyone else not muddy. And when the teacher says, oh, there's one muddy kid, then that kid will, of course, realize. So in that case, in the first round, someone will step forward. Now what about k equal to 2, right? If k is equal to 2, and the teacher says, okay, you know, there exist muddy kids, and if, let's say, I'm muddy, I don't really know, because, you know, I see one other muddy kid, so I won't step forward in the first round. But, you know, the other kid is doing the same reasoning. Like, if the other kid didn't step forward in the first round, it must mean that that muddy kid also saw someone muddy. So that means if no one stepped forward in round 1, there must exist at least 2 muddy kids. So now in round 2, because I saw only one other muddy kid, I know that I'm muddy too, and that I would step forward. And you can do this inductively for any k.
So is there an assumption here that the kids who are not muddy, they know for certain that they're not muddy, so they never question their...
No, they don't. The point is, I don't know if I'm muddy, right? The only information I know is whether everyone else is muddy.
I think it's because like, if they're not muddy, then by the time everyone step out, they know they're not muddy already.
Yeah,
so it's like because they're one step delayed.
Yeah, so like k equal to 1 is trivial. Like, I think you can just work your reasoning through k equal to 2. Like, for k equal to 2, the critical thing to realize is if there are 2 muddy kids, like, if no one stepped forward in round 1, did I drop? Hello?
Your screen dropped.
My screen dropped. Okay, this time is not my voice. That's okay, we don't need the screen anymore. So if, let's say, no one stepped forward in the first round, it means every muddy kid must see at least one other muddy kid, right? Because if the muddy kid doesn't see anyone else muddy, they would have stepped forward in the first round. So if no one stepped forward in the first round, it means every muddy kid must see at least one other muddy kid. So that means, you know, in round 2, I already know there exists at least 2 muddy kids. And if I see only one other muddy kid, I realize I'm muddy too. So then I will step forward in round 2. And then you can just build it up through induction. So it is a little bit like Dolev-Strong, right? Because, like, you know, in the other case, it's like in round f+1, you reach common knowledge. But here it's like, oh, you're in round k, you'll reach common knowledge. Okay. So I hope this was fun. I can stay a little longer if you want to ask questions, but otherwise we are all good. We finished early today.